Hello, this is Dr. Wang Yuan from Institute of High Performance Computing under the Agency for Science, Technology and Research in Singapore. We are pleased to share our latest work in federated learning, which has been accepted to this year's CVPR conference. Let me first briefly introduce the background and our general motivation of this work. As we know, the traditional FL methods require clients to update their local models based on a globally aggregated server model. In this process, sharing the local model or gradients is prone to gradient leakage attack and may not be communication efficient if the model size is large. Additionally, local model updates can lead to forgetting knowledge learned in previous global model, causing client drift and inferior convergence performance in non-IID scenarios. To address the limitations of traditional FL methods that rely on aggregate then adapt framework, we came up with FedAF, a novel model aggregation-free FL algorithm. In this framework, clients collaboratively learn compact sets of synthetic data, aka the condensed data. The server subsequently trains the global model, using the condensed data and logits received from the clients. The model is trained only at the server, while clients instead focus solely on learning and sharing the condensed data. The current model aggregation-free methods have two limitations. First, significant cross-client data heterogeneity can compromise the quality of locally learned condensed data, adversely affecting the global model training. Second, relying exclusively on the condensed data for global model training can result in reduced convergence performance and robustness, especially when the quality of the received condensed data is suboptimal. To fill these gaps, our FedAF enhances the learning of condensed data by utilizing broader peer knowledge through the collaborative data condensation scheme. Our method also improves global model training with the local global knowledge matching scheme, utilizing more global insights beyond just the condensed data. With these two new schemes, our method considerably improves the convergence performance over traditional FL methods in the context of non-IID cross-client data distribution. Now let's look at a little bit more details of our method. In each round of FL, the clients start by downloading the latest global model and the class-wise mean logits from the server. The clients then learn and update the local condensed data by evaluating a distribution matching loss and a regularization term named collaborative data condensation loss, aka the CDC loss. The distribution matching loss takes the feature representations from both the original data and the local condensed data as the input. The CDC loss is used to capture the distance between the distribution of the logits generated from local condensed data and the logits from the original data, including both a client's local original data and that owned by other clients. This scheme allows each client to leverage the broader knowledge in the data of other clients. In this way, clients can learn condensed data with the assistance of global insights shared by peer clients and avoid the pitfall of biased matching towards their local data, facilitating the learning of higher quality condensed data. Once the clients complete the local update, each of them sends the condensed data and the mean logits for each class of its local original data to the server. Upon receiving this information from clients, the server follows on to update the global model by optimizing a training loss that combines traditional cross-entropy loss with a local global knowledge matching regularization term, aka the LGKM loss. The LGKM loss evaluates the KL divergence between the distribution of soft labels from the condensed data and the distribution of soft labels from the class-wise mean logits extracted from clients' original local data. Augmented by the LGKM regularization, the server gains a more comprehensive understanding about the original data distributed across clients. Therefore, the trained global model better retains knowledge acquired in prior rounds, facilitating improved model accuracy and accelerating convergence speed, especially when condensed data is less optimal due to strong cross-client data heterogeneity. Now, let's take a quick look at the experimental results we obtained for benchmarking with several state-of-the-art baselines. We used FashionM-NIST, CIFR-10, and CIFR-100 dataset to set up our label skew non-IID scenarios, where 10 clients are involved at all times during federated learning. We adopted the Dirichlet distribution to split the data for each client with a control variable, alpha. Smaller alpha values indicate stronger cross-client data heterogeneity. We tested over 3 alpha values for each dataset. The results show that our Fed-AF improves performance over Fed-DYNE, the leading aggregate then adapt baseline, by up to 19.43%, 13.70%, and 17.74% on CIFAR-10, CIFAR-100 and Fashion-M-NIST respectively. Besides, Fed-AF also consistently outperforms Fed-DM, another similar approach, with advantages of 4.87%, 4.56%, and 2.17% on CIFAR-10, CIFAR-100 and Fashion-M-NIST respectively. As for the convergence speed, our method surpasses all the other baselines, particularly under significant data heterogeneity. For example, on CIFAR-10 with an alpha value of 0.02, Fed-DM reaches an accuracy of 60% in 15 rounds, while our method achieves this accuracy in just 3 rounds, representing an 80% increase in convergence speed. We also benchmarked our method with other baselines in a feature skew non-IID scenario using the domain net dataset. We have followed the same data split profile as Fed-BN. Similar to the tests for label skew scenarios, our method outperforms most of the other baselines in the accuracy of each domain and performs best in the average accuracy across domains. Additionally, our method demonstrates superior convergence speed in the feature skew environment. Apart from the main results, we have also conducted several ablation studies, such as the experiment for different values of IPC or image per class. Basically, the larger IPC, the higher performance one can achieve, but the increased trend quickly saturates when IPC is higher than 50. This is because the density of knowledge embedded in condensed data becomes lower while the amount of original data is fixed. We also studied the individual impact of the CDC and LGKM scheme in our Fed-AF. The results show clear evidence for the effectiveness of these two schemes. In the previous results, we used a convnet of 3 convolutional layers. We also tested our method using ResNet 18, and the results similarly showed superiority over other baselines. In addition to convergence and accuracy, we also analyzed the communication cost. The communication overhead of our method is invariant to the model architecture, making it much more communication efficient when the number of classes is small or the model size is relatively large. Finally, here we show some examples of the learned condensed data. They appear very blurred and retain almost no distinguishable features of original images, showing good visual privacy. In fact, a recent theoretical study regarding data condensation showed that smaller image per class values lead to good robustness against membership inference attack. For the robustness against reconstruction attacks, such as the DLG attack, we also conducted experiments that show that one cannot reconstruct the original images by hacking the model trained on the client's learned condensed data. Thank you for watching. We warmly welcome any questions and constructive suggestions.